In this video, I'd like to look at some slightly more complicated graphs of exponential functions. And recall in the last video, we looked specifically at the function y equals 2 to the x power. And a lot of times you might see this called a parent function, since it's probably the most basic exponential function we can write. So a lot of times it's useful to think about the parent function and what happens to it if I do certain things to it. So in this case, I'm multiplying by 3 on the outside. So just so you can get a better idea of what's going on, let me quickly graph this parent function, and then we'll look at what happens compared to this function. So with this parent function graphed, what I like to do is think about what happens specifically to this point here, this y-intercept, or essentially the x value that makes this variable exponent 0. So whenever I do transformations to the parent function, I will often look at what happens to this point. So right now, compared to the parent function, we're at 0, comma 1, but now we're multiplying all y values by 3. So instead of being at 0, 1, it's now at 0, 3. Instead of being at 1, comma 2, it's now at 1, comma 6. And same idea for these negative values. Instead of at negative 1, 1/2, we're now at negative 1, 3/2, and so on. But the asymptote will remain the same. There's still no x value you can put in here that'll make y equal to 0. So again, it's going to hug along the x-axis, but then essentially what happened by multiplying by 3 is that it stretched the function vertically. So let me write that down. We have a vertical stretch by a factor of 3. Now, one question you can ask yourself is what happens if I multiply by a negative number? So in this case, let's say y is minus 3 times 2 to the x. So we're still looking at this orange one here, but now all of the y values are negative. So instead of being at 0, 3, now I have the opposite of that, so I'd be at 0, minus 3. And instead of being at 1, 6, I'll be at 1, minus 6. And again, we can just connect these, but basically what you'll see is we have a reflection about the x-axis. So let me write that down. We have a reflection. So essentially all of the y values are now the opposite of what they were. And you can even ask a further question. What happens if I multiply by something between 0 and 1, like a half? And the effect is the same. Essentially, all the y values will now be cut in half. So compared to this parent function, when we're at 1, 2, now it would be at 1, 1. And instead of being at 2, 4, it would be at 2, 2. And instead of 0, 1, it would be at 0, 1/2. So essentially just flattened it out, or we can say it shrunk it by a factor of 1/2. So now that we've essentially looked at what happens when you multiply on the outside by a number, let's look at a couple different scenarios. So now, in this orange scenario, I'm taking my parent function, I'm adding 4. And so essentially what that does is essentially adds 4 to all of my y values. And remember, we had an asymptote for our parent function of y equals 0. It never crossed this x-axis. But when I add 4 to that, it essentially shifts the asymptote up 4 units. So now I have this asymptote at y equals 4. So our function cannot cross this line, and it's going to be the same exponential function as our parent function, but like I said, everything is shifted up 4 units. So remember, you started with the parent function going through at 0, 1, but now you're going to go through at 0, 5. And instead of being at 1, 2, you're now going to be at 1, 6. But it's going to be the exact same looking function, it's just shifted. And now looking at this green function here, we have to ask ourselves what happens when I add or subtract on essentially the inside of our function, or in our input of the function. And the way I always think about this is I think about which x value makes this expression 0. And in this case, it's positive 1. So since it's positive 1, that tells me we're going to shift everything to the right 1. So let me write that. So with this function, we essentially start with our parent function, just like normal, but everything is now shifted 1 unit to the right. So instead of being at 0, 1, it's now at 1, 1. And instead of being at 2, 4, it's now at 2, 2, because this point at 1, 2 is shifted over. And everything else looks the same. It's just the entire graph is shifted to the right 4 units. And if you want, you can find your y-intercept. That should be an x value of 0, so you can plug 0 in here. You get 2 to the minus 1, which is 1/2. So in summary, adding and subtracting on the outside shifts it up or down. And it's very straightforward. If it's adding, you go up. If it's subtracting, you go down. However, with x values, it's essentially the opposite. If you're subtracting 1, that means you go to the right one. And if you're adding 1, that would mean you go to the left one. But I advise you to consider it, like I mentioned, where you think about which x value makes the expression 0, and if it's positive, that tells you you go to the right. And now let's move on to a slightly more difficult example. So now we're subtracting x on the inside. And whenever you see this, it's important to rewrite it by factoring the negative out. So we have 2 to the minus x minus 3. And once you do this, this will give you a much better idea of what's happening to your function. So first of all, think about what it means when you have a negative in your input. And when we had a negative on the output, right, when we had it in front, then that reflected it about the x-axis, or essentially all the y values were now the opposite. But when you have a negative on the inside, it's essentially the opposite reflection. Now we're reflecting about the y-axis. So essentially all the x values are now opposite. Or what it does, like let's say this was our function, and when we put a negative in there, all that does is just flip it about the y-axis. So that's the basic idea of having a negative inside. But when you have a scenario like this, it's always important to factor that negative out, since you have to factor it out first before you consider how it shifts left or right. And once you factor it out, now we can think, well, which x value makes this expression 0? And that would be positive 3, so that tells us to go to the right 3 units. And like I said, the negative tells us to reflect. And we're reflecting about that y-axis. So what I usually do with problems like this is I again think about my parent function. Remember, y is 2 to the x. And I know it goes through at 0, 1. And basically, I want to figure out how does this point transform and how do I end up with this function. So first of all, a reflection about the y-axis actually does not do anything to this because it's on the line of reflection. So then we just have to shift it right 3 units. So we're over here. And now a normal function would look like this. That would be a normal growth function. But since we reflected it, we expect our function to come down like that. But we just have to figure out the exact points for that. So what I recommend doing is either plugging in a really obvious value, like x equals 0, or picking a point right next to it. So I'll pick the point 2. So then when I plug in x equals 2 to this function, I get y is 2 to the first power. So 2 comma 2 is a point there. And if I want, I can continue plotting points, though 2 is kind of enough to give you the general idea. And we know since we didn't add or subtract on the outside, that my asymptote is still at y equals 0, or this x-axis. But just for safe measure, I'm going to plot a third point. So let's plot x equals 1. So if we plug 1 in there, then y is 2 squared. So 1 comma 4 would be a part of the graph as well. And if we plugged in 0, we get 8. So it shoots off pretty quick. So that would be somewhere maybe up there. But that'll give you kind of a general picture of what our function is starting to look like. So it looks something like that, though this is honestly a little bit sloppy. And remember, with these, you can always check it with the graphing calculator. You want to know how to do this by hand, but it's important to always check your work if you get the chance. So in summary here, if you're ever subtracting x, it's important to factor out the negative first and then consider how the transformations are made.